In this video, we will expand on the system of two connected masses, but this time add friction to the problem. So be sure that you've watched the connected masses video carefully before viewing this video. Now, consider the same scenario with two masses connected over a frictionless pulley by a cable. The mass of both the pulley and the cable are negligible. Mass 2 is sitting on a flat horizontal surface that is not frictionless. Let's now apply Newton's laws and analyze the forces involved. Let's begin as we did with the connected masses video by looking at the forces acting on each of the mass in our system, starting with mass 1, which is hanging vertically. Mass 1 has a force of gravity acting on it, which we will call weight 1. Mass 1 is connected to a cable which pulls up on it with a tension which we'll call T. If mass 1 is stationary, then the tension on the cable will be equal to the weight of mass 1. However, if mass 1 was to move, the only logical direction is downwards. So the direction of the acceleration, if there was any, would be down. We don't expect mass 1 to move sideways either, so there is no net force in the horizontal direction for mass 1. So let's now write out the equation for Newton's second law for mass 1. Again, we will define the downward direction as positive so that we have a positive acceleration. So Newton's second law for the vertical direction gives us the net force being equal to the weight of mass 1 minus the tension, which of course is equal to mass 1 multiplied by the acceleration if there was a net force. If there was no net force, then the acceleration would be 0. Now let's look at mass 2. As mass 2 is sitting on a horizontal surface, its weight is pushing down on that surface due to gravity. Naturally, the surface pushes back up via the normal force in accordance with Newton's third law. The net result is no movement in the vertical direction for mass 2. So the force equation for mass 2 in the vertical direction is the weight of mass 2 minus the normal force exerted on mass 2 being equal to 0. Now mass 2 is connected to mass 1 by the cable, which has tension in it. So the cable is pulling at mass 2 to the left with the same tension as applied to mass 1. These two tensions at each end of the cable are the action and reaction forces due to Newton's third law and have the same magnitude but point in opposite directions along the cable. Since the two masses are connected by the cable, if there is any movement in mass 1, then there is a corresponding movement in mass 2 because mass 1 pulls on mass 2. So the acceleration experienced by mass 2 will be the same as that experienced by mass 1, but the direction of the acceleration will be to the left. So if there's acceleration to the left, then what is the direction of friction? If there's an acceleration to the left, then the friction between mass 2 and the surface will try to oppose the motion by applying a resistive force in the opposite direction, that is, to the right. Since we expect any movement will be to the left, let's call this direction as positive. So along the horizontal direction, we have tension directed to the left, which is positive, and frictional force directed to the right, which is negative. So Newton's second law for mass 2 along the horizontal direction is tension minus the frictional force to give us a net force being equal to the product of mass 2 and the acceleration, which is in the positive left direction. Again, we're going to combine the equation for mass 1 in the vertical direction with the equation for mass 2 in the horizontal direction and eliminate the tension from the equations. We can do this by solving for the tension in equation 3 and substituting it back into equation 1. So the equation for mass 1 becomes the weight of mass 1 minus the tension, which is equal to the product of mass 2 with acceleration plus the frictional force, to give us a net force equal to the product of mass 1 and acceleration. Now we can transpose this equation to solve for acceleration, which gives us the acceleration being equal to the weight of mass 1 minus the frictional force divided by the sum of mass 1 and mass 2. And of course, the weight of mass 1 is equal to the product of mass 1 and acceleration due to gravity. So we now have a solution for the acceleration of the connected masses, which is dependent on the mass of the two objects and gravity as well as friction. Let's analyze this solution in a bit more detail. So we can see that the solution for acceleration is very similar to that derived for the connected masses without friction, except with an extra frictional component to it. But the analysis of the acceleration is a little bit more complicated. Let's look at the case where there's no mass 1. If there's no mass 1, then there's no tension on the cable pulling at mass 2. Mass 1 in the equation would be 0, and the equation reduces to minus the frictional force divided by mass 2. This gives us a negative acceleration, suggesting that mass 2 will accelerate to the right in the absence of mass 1. This would not make sense. To understand this, we need to remember that static frictional force increases from 0 to some maximum value, and it's only when the applied force, which is the tension in the cable in this case, is greater than the maximum static frictional force that the mass will start to move. So if there is no tension, then there is no need for there to be any frictional force. In this case, the frictional force reduces to 0, and thus the acceleration is also 0, which makes sense. So the acceleration equation is only valid when the tension is greater than the static frictional force. Of course, the maximum tension occurs when mass 1 is not accelerating and the tension is equal to its weight. The final thing to note is that if there is acceleration, then friction changes from static to kinetic friction, which is governed by the coefficient of kinetic friction instead of the coefficient of static friction. Frictional force is equal to the coefficient of friction multiplied by the normal force acting on mass 2. Since mass 2 is on a horizontal surface, then the normal force acting on it is equal to its weight. So if our masses are 10 kilograms each, and the coefficient of kinetic friction between mass 2 and the horizontal surface is 0.25, then what is the acceleration of the masses?